A brief introduction of metamaterials by Group B9.
Definition: a synthetic composite material with a structure that exhibits properties not normally found in natural materials. A common property is the negative refraction index, meaning that electromagnetic radiation, such as light, will not refract through the material. It will rather bounce off or even bend around the object. Relevance to electromagnetism. While the properties of metamaterials are not limited to manipulation of electromagnetic radiation, they provide many opportunities for innovation in this field due to the effect that a material may have both the electrical and the magnetic portion of a wave. The ability to manipulate both of these spectrums allows for a large range of uses in electromagnetism depending on the design of the material itself.
Metamaterials have a variety of applications in today's society, only a few of which we'll briefly cover. The first application is a superlens that is capable of viewing extremely small objects. This concept will be elaborated on in the next slide. Due to the bending of electromagnetic radiation that was previously mentioned, cloaking of an object is possible using metamaterials. It has been accomplished in the microwave and infrared spectrums, and visible light is not too far off. Additional uses include anti-ice, anti-fog, solar enhancement, laser protection, enhanced antennas, or an electromagnetic radiation absorber.
One example of metamaterials being used is in superlenses. A superlens is created by using metamaterials to create a lens that goes beyond the diffraction limit. The diffraction limit is the maximum resolution of a lens due to imperfections in the lens or misalignment of the lenses. A superlens, such as those in electron microscopes, allow for sub-wavelength imaging, which provides the ability to see things smaller than the wavelength of visible light. This is achievable by having an interface between two lenses of opposite refraction indexes, one positive and the other negative. Metamaterials are used to create lenses which allow us to view microscopic objects.
A metamaterial is an object that abuses the intrinsic properties of a material and an arrangement of structural elements, which can be viewed in the pictures below, to cause specific and unusual effects on electromagnetic or other properties. As previously mentioned, the properties of a metamaterial arise from both the base material and the geometrical arrangement. A common arrangement is where the size and spacing is much smaller relative to the spatial variation of the applied field. Most, if not all, natural materials have a positive permittivity and permeability. Metamaterials break this norm and can be sorted into different categories that will be explained shortly. We will then focus on two of these categories.
Almost all materials can be characterized by these two properties: the electric permittivity epsilon and the magnetic permeability mu. The thinnest materials found in nature is air, which is denoted by epsilon naught and mu naught, which is also used to find the relative permittivity and permeability of a material, shown in Formula 1. The relative permittivity and permeability also define another important material parameter, the refractive index, shown in Formula 2. Most materials found in nature have a positive value of permittivity and permeability and occur at a certain discrete points on the line mu equals mu naught and epsilon greater or equal to epsilon naught. There are also several lines and points that indicate special material properties. For example, when mu equals negative mu naught and epsilon equals negative epsilon naught, this represents an anti-air region which can produce a perfect lens. Another special property is on the line mu equals epsilon, which represents a region with impedance matching material, which have perfect impedance matching with air, resulting in no reflection. Metamaterials can be subdivided into three types: the homogeneous metamaterials with periodic arrangements of metal atoms, random metamaterials with random arrangement of metal atoms, and inhomogeneous metamaterials, with meta-atoms arranged based on certain parameters. Among them, the homogeneous metamaterials can be categorized into different groups: the double negative metamaterials, the double positive metamaterials, and the single negative metamaterials, which contains epsilon negative metamaterials and mu negative metamaterials. There is also a special kind of metamaterial which has permittivity and or permeability approaching zero, known as zero-index metamaterials.
The first category of metamaterials is the double negative index. These metamaterials have both a negative permittivity and a negative permeability. This results in the negative index of refraction. In optical materials, this causes wave propagation to travel backwards. The second category of metamaterials is the single negative. These metamaterials either have a negative permittivity or a negative permeability, but not both. Combining one of each type in this category can allow them to act together as a single double negative metamaterial. When a double negative interaction is formed, the metamaterial may be used to manipulate the refractive index and change the way that electromagnetic waves interact with their structure. This is what allows for many of their applications.